Hello everyone, I'm Longxiang Wang from City University of Hong Kong. Today I will present our paper Alert, Machine Learning Enhanced Risk Estimation for Databases Supporting Encrypted Queries. Dynamic Searchable Symmetric Encryption, commonly referred as DSSE, enables clients to search their encrypted data on a third-party server without decrypting it first. In a nutshell, DSSE supports three fundamental operations. The first is setup. The client's encrypted data file collection, transforming it into an encrypted database, which is then uploaded and stored on the third-party server. The second is query. When the client wants to retrieve specific files, they raise an encrypted query to the server. The server will correspondingly return the encrypted files as a response. The third is update. The client can add or delete encrypted files from the database. This capacity introduces dynamic characteristics that distinguish the DSSE from static searchable encryption schemes. While encrypted database is encrypted, they have been demonstrated to be vulnerable to leakage abuse attacks. The figure shows a typical leakage abuse attack. The client proposes queries to the server and correspondingly return with encrypted files. The adversary passively monitors the querying process, aiming to reconstruct the user's original queries based on structural equivalent leakages before and after encryption. We observe that existing defensive approaches, such as padding or the use of oblivious RAM, often struggle to balance the trade-off between security effectiveness and system efficiency. So we wonder, is there a way that can prevent LAAs without sacrificing system performance? We observe that LAA itself can naturally serve as a mechanism for assessing leakage risks. As shown in the figure, when the client submits a query, a simulated attacker can quickly evaluate how risky the query might be. If the system detects any potential risks, it can immediately freeze the query and wait for further instructions. This approach effectively isolates real attacker from actually being able to monitor risky queries in real time, thereby preventing the real attack. Previous LAAs and leakage analysis works have primarily focused on exploring new vulnerability vectors rather than computational efficiency. Our experiments demonstrate that these approaches are hard to achieve the real-time performance requirements that are necessary for practical query risk assessment tools. Then, our problem can be narrowed down to how to build a LAA that achieves comparable performance while significantly reducing risk assessment latency. To achieve real-time requirements, we reformulate a previous studied heuristic optimization problem to machine learning multi-classification problems. Specifically, previous LAA approaches first extract auxiliary patterns from the auxiliary data that aligns with leakage patterns, and then iteratively match auxiliary and the leakage, aiming to minimize the distance between auxiliary and the leakage patterns. This method can be progressively enhanced by gradually incorporating more prior knowledge to achieve optimal recovery effectiveness. However, we observe that this approach requires repeated iterative optimization, resulting in significant risk assessment latency. When new query is proposed, the system needs to recalculate the entire risk assessment, further increasing proposed time. We reformulate the heuristic optimization problem as a machine learning multi-classification task. The reason for choosing machine learning is that we can transform the time-costly risk assessment progress into offline model training, therefore saving time-sensitive online risk assessment. Specifically, we train the machine learning model on auxiliary data to learn curious patterns. In the online environment, it only needs to perform inference on the leakage patterns, which significantly reduce program runtime, achieves almost real-time monitoring. In constructing the system, we found several types of challenges. First, in SSE, most structural leakages are query-dependent, often spanning multiple queries, which complicates the alignment between leaked information and the data used for training. Second, a large number of classes affects both model performance and the leakage pattern updates. In this paper, we propose several approaches to solve these challenges. To address the feature misalignment issue in training data preparation, we specifically tackle two types of inconsistencies. The first inconsistency stems from variation in the number of files collected at different timestamps. The scale of file collected at each timestamp can differ greatly and change as the database accumulates, leading to imbalanced features during model training. To mitigate this, we normalize each curious factor into a sequence with mean 0 and the standard deviation 1, thus eliminating the influence of absolute values. The second inconsistency is that the concurrence feature depends on the order of queries, which is not accessible in real targeted databases. For example, in the two matrices shown in the figure, the matrices are actually identical, but due to different query orders, they produce complete different features. To address this, we resort the vectors in the training data to remove order information to ensure its alignment with the test data. The second major challenges arise from the task of recovering queries in the databases that typically contain a large number of queries, often in thousands. Training a single model is suboptimal due to the large number of classes, which resulted in an excessive number of model parameters, leading to increased latency and a low query recovery performance. To address this, we employ a dynamic programming algorithm to cluster queries based on their volume information, and then train a separate model for each cluster. We need to note that dynamic clustering mechanism is not always necessary in the risk assessment progress. It serves as an extension of alert, and it is utilized when the targeted database contains a sheer quantity of classes. Specifically, we analyze queries' historical volume rankings to determine clustering thresholds. By examining the temporal variations in these rankings, we identify stability patterns across different queries. These stability patterns, in turn, guide the dynamic establishment of clustering boundaries, which reflect the stability variance of queries. In the online risk assessment phase, we observe that when the number of timestamps is large, computing the co-occurrence matrix costs too much time. To address this, we propose an optimized co-occurrence matrix computation method that leverages previous co-occurrence state. Specifically, when a new query is proposed, the original method requires one matrix multiplication of size n times k and k times m. Instead of those matrix multiplications, with our optimization, we only need to do a much lighter vector matrix multiplication and a simple vector multiplication. After calculation, we take the previous co-occurrence matrix that we already had and combine it with the newly computed vectors to form the updated co-occurrence matrix. As a result, the time complexity is reduced from OKN squared to OKN. Our evaluation results demonstrate the effectiveness of alert. We compare alert with 3 state-of-the-art LA approaches, Jigsaw, IHOP, and RSA, all of which have been published in USENIX Security. We selected these baselines based on their query recovery performance and system efficiency. Under settings without time constraints, it achieves a 14.5-fold speedup with only 5.2% recovery loss compared to the second fastest LA approach, Jigsaw. Furthermore, we found that alerts exhibits greater stability, achieving an even higher average recovery rate than Jigsaw on the New York Times datasets. In the low latency scenario, which corresponds to our real-world setting, alerts significantly outperform other LA approaches. With a runtime of 5.4 seconds, alerts achieves a median query recovery rate of 86.3%. We're also maintaining a lower interquarrel range compared with other approaches. Even with a strict time limitation of 1.8 seconds, alerts still maintain a recovery rate of 66.8%, showing its efficiency. Furthermore, alerts demonstrate robustness even in more challenging scenarios. Compared to Jigsaw, alerts maintain higher median recovery rates when the keyword universe is extremely large. Under a keyword universal size of 7,000, even when Jigsaw is configured for its fastest operation mode, it still requires over 20 seconds to recover all queries, which prevents larger scale comparison experiments with alert. Finally, alert also outperforms previous state-of-the-art LA methods under various pattern countermeasures. Notably, when facing cluster-based countermeasures, alert's recovery rates dropped by only 4.5%. It's much less than other LA approaches. This is due to alert's effective modeling of overall sequence features. All of our experiment datasets and scripts are open sourced. You can access with the link below. If you have any other comments about our paper, you are welcome to send your comments to this email. That's all we want to present today. Thanks for your listening.